I want to talk about optimizing breeding using selectiongain package of R. And this selection package is very helpful to optimizing breeding activities along the breeding pipeline. Indeed, a breeder is given a fixed budget, and he or she needs to use this budget to do breeding activities as stipulated. A problem arises when a breeder needs to know the optimum number of individuals to select in each stage, and also the optimum number of locations to use in evaluating materials, and similarly the optimum number of replication and other activities to take and other activities along the breeding pipeline while considering the fixed budget. So this selection gain package comes handy in helping a breeder make decision on the optimum number of individuals to select, an optimum number of locations, or optimum number of activities that are carried along the breeding pipeline with regard to the budget that is available. The first thing to do is to install the selectiongain package. You type install.packages as indicated here. Then you load the selectiongain package into the library by typing library and indicating the package you want to load the library, that it is selectiongain package. Then you run. The next important thing to do is to state your budget. For instance, here the budget is 200,000 US dollars. One thing you need to do here is to convert this budget into the number of plots that can be evaluated by this budget. For instance, a cost of evaluating one plot is 20 USD. Therefore, 200,000 USD evaluates 10,000 plots. Therefore, the budget is 10,000, and this budget is the number of plots that can be evaluated. Keeping in mind that one plot is evaluated using 20 USD. The next thing is to know the variance component for GCA and error. This can be got from the previous studies which have been done, and this will include this value here, which is the variance component for the genetic effects, GCA for genetic effects. This value here is the genotype by location interaction. This it's VC, GCA for location by genotype interaction, and this one here is genotype by year interaction, which is 0 because it's not found here. The breeder does not have here right away now. And this one is the interaction of genotype by location by year. By the fact that there was no here, this value here, it means this one is not available. And this one is the VC for variance component for error. Then we come to variance component specific combining ability. These are a genetic effect, then followed by genotype. This here 2.4 is genetic effect, followed by 3.2, which is interaction of genotype by location, followed by interaction of genotype per year, and interaction of genotype by location per year, which is not available. When it's not available, you put a 0. Therefore, 0 here means that this data is not available. After this, the next important thing is to state the NF, which is the number finally selected. This is the number you would like to select finally. Here is 10. We have chosen it to be 10. So after stating these four components here, you run them. Then we need to run the analysis so that we can get the optimum number of individuals or optimum number of activities that can be done along the breeding pipeline. And to do this, we have two types of analysis. Analysis using phenotypic selection and analysis using genomic selection. And I want to tell you that this is a two-stage selection. That means there is evaluation. There's a evaluation at two stages. We use small stage optimum search function to run this analysis. Small stage optimum search function is a function of selection gain package. Now here we have different codes that I'm going to explain and in this script. Mass save is marker assisted selection efficiency. We put it NA because we're not going to use any marker selection or genomic selection. Alpha.nursery is the proportion of individuals which you intend to select from a nursery. So you don't select 100% due to maybe diseases or other factors. So here we have chosen to select 0.25 of the nursery. Here, fidgets A and E. This variance general combining abilities and error variance component is this one, VGC error. So this one here is this one as we stated here. VSCA, this specific combining ability variance, is this one here. This one here is this which we specified here. Now we have other components here: cost.nursery, cost prod, and cost test. These are very important. So cost.nursery is the cost which you incur in the nursery. We have two kinds of costs. This one is 4 and this one is 1. Here, 4 is the cost which you use for example, in developing an inbred line or in a double haploid line. You get a nursery and you develop from that nursery a double haploid line, for instance, in maize breeding, or an inbred line. This is 4 is the cost of developing one inbred line or one double haploid line. After developing, this one is the cost of evaluating one double haploid or inbred line in your nursery. So this one is developing, this 4 here is developing, and this one is evaluating. And this one, remember we said one plot is evaluated using 20 USD. So here one means that you are going to use 20 USD here to evaluate one inbred line or double haploid line. And here 4, it means 4 times 20, that is 100 USD in developing one inbred line or one double haploid line. So this 4 is the cost of developing a double haploid or inbred line in a nursery, and 1 here is the cost of evaluating one inbred line. Cost of production, assuming that this is maize breeding or wheat breeding, cost of production is the cost which is incurred in developing hybrids. Here we have 0 here means we are nothing's done here. There's no cost at this stage. Then we have 2 values here. That means this is 2 stage. There's production here, stage 1, and there's production of hybrid in stage 2. 4 here stands the cost of producing one a hybrid in stage 1, and 4 years times the cost of producing one hybrid in the other second stage. Cost of testing, you have to test these hybrids that was developed here. Cost is one in of selecting, or this one which is used to test or to evaluate the the hybrids that were developed in the first stage. And then we have the second stage of testing or evaluation. Here we have two stages of production, and these two stages are also evaluated in two stages or tested. So this one tested this here, and the other one, last one, tested this stage here. NF is a number that is finally selected. NF is NF because we specified it here. Budget is budget. We specified our budget is 10,000 plots. So 10,000 plots is equal to 200,000 US dollars because we did some calculation here. We place our budget. Then another thing that you need to understand is here, we have N2 grid here, N3 grid. Then L2 grid, L3 grid. T2 grid and T3 grid. So M is the number of hybrids. L is the number of locations. T is the number of testers. R here, down here, is the number of replications. Let's start from N2 grid. N2 grid is the number of hybrids that need to be evaluated. You have developed hybrids here, and you need to evaluate it. What do you desire? Here you put your desires. You have developed maximum 4,011 hybrids, which you need to evaluate. 4,011, this is the maximum number. And 11 is the minimum number which you want. You want minimum number. 30 is the interval of increase. For example, the model will run between 11 and 4,011 to give you the optimum number of the optimum number of hybrids to test. So minimum is 11 and maximum which you have is 4,011. And the model will evaluate by increment of 30. That means 11 plus 30 is 41. After 41 plus 30 is 71, and so on until 4,011. And between 11 and 4,011, the model will give you the optimal number which you need to have a higher genetic gain with regard to your budget. Because we have developed the first stage, we developed, and we are going to evaluate at the first stage. The N2 grid is the number of individuals to be evaluated at the first evaluation. N3 is the number of individuals to be evaluated at the second evaluation. So I hope you have understood here. Let's go to second evaluation. You see, this is the cost, and here now we are optimizing the number that we want. Our model will run and tell us the optimum number here. Also, the model is going to run and tell us the optimum number. NF is just 10 here because we have indicated here. L3 is the number of locations that you intend to run your evaluation. Here is the first evaluation. Here is the second evaluation. We have the maximum we want is 10 and the minimum is 1 at increment of 1. So the model will run between 1 and 10 and give you the optimum number that is going to give high genetic gain considering your budget. And this is the number of location in your second evaluation. Then we come the testers. This is the number of testers in your first here when you are producing the hybrid, you use testers, and the second production is the number of testers that you use. 1 is the minimum, 5 is maximum at increment of 1. Then the model will run and give you the optimum number of testers. The same applies to here. T2 free, this is a logical value. T, the vertex means is testers. When it's false, the cost of the T2 and T3 will be taken separately, but when it's true is the total number of testers, the cost of total number of testers will be accounted for. R2 in the first evaluation, this is the number of replication in the first evaluation, and the number of replication in the second evaluation. Here is 1, that means you are not replicating. There's no replication here. But if you want to 2, 3, you just indicate here. I think this was done because we have number of locations here. And so that considering the amount of money you have. Alg is algorithm. You can use Miwa. It's recommended you use this Miwa. But the default is this GNC press. This one is the default. You can use this Miwa. And details that it gives you the result of all grids if you put true. But if you give false, it gives you the most optimum grid to consider, of which we take the most optimum. So that's why it's false. It's going to give you only the optimum grid, not others to select from, because obviously you're going to select the most optimum. Figure false is just it's not going to draw any figure. This one you have understood it. Before I run, let me explain this one for genomic selection. It's the same. It is two-stage selection. You can see marker assisted deviations. This is the predictability, 0.8 of your genomic selection. You get the predictability 0.8. Alpha nursery 0.25 as we got. Variance component for general combining ability and specific combining ability is the same. Cost dot nursery is 4 and 1 is the same, just like here. Explained it. Cost of production is 0, and for 0, this means we are not going to produce twice. We are producing only once. This is because we are going to have genomic selection, assuming that it's very efficient. Cost of tests is 4, 1. Now we don't have this here, the last one. We have 4 because this is a value of genotyping your materials. When you want to evaluate using genomic selection, you genotype. Then after genotyping your material, you apply the genomic selection model to do your selection. And this one is, we have one phenotypic evaluation. This means we use genotypic selection. We don't do phenotypic selection. But lastly, at the end, we use one phenotypic selection. But if you highly trust your genomic selection, it can be one stage here. You use only this genomic selection. But here we are going to use genomic selection and the one phenotypic selection. This is the cost of genotyping, as I said. And then you apply your prediction model. Then NF is the NF that we knew, the number final selection budget. T2 freeze true, as I said. N grid, you can see N2 grid, L2 grid, and T3 grid, we have values here. But you can see L3 grid, we have 0, 0, that we have 0 number of locations you want to start with, and 0 number we want to finish at interval 1. That means there's no location in the second evaluation because it's not there. You don't have other production, the second stage of production to evaluate. Also test that we don't have the second the hybrids level of hybrid production to use your testers here, but we have this one here, the first evaluation use here, and then the rest remains. Then you run, for example. So now let's first run this phenotypic selection. You see how the result comes. The results here. Let me also run this code for genomic selection, as I explained. So as it's running, let me explain this result for phenotypic selection. This test results. These are the results. The gain from that budget. Oh, it's here. Let's start from the phenotypic selection. This the gain. You see gain here. It gives you the optimum gain you are going to receive along the years in your breeding scheme. If you are taking 10 years, this is the gain you are going to get it, within 10 years. Or if you are taking 5 years, this is the gain. For instance, this scheme goes for 5 years, and these are the gain you get in 5 years. So you can divide by 5 to get the gain each year, which will be 1 point something like 1.1 for the gain in a year. So NF is the number of final selection, as we specified, and the initial number NIN is the initial number which you select. You select 1,124. These are the optimum number you want to select. And the number you are going to select in the first evaluation is 281. And N3 is the second evaluation. You are going to use select 39. And the 40, the 10.8 is 40. And look, you are going to use in the first evaluation, use 5 location. The second evaluation, you use 6 location. In the first in the first stage of producing hybrids, you use 1 tester here, while in the second stage you use 5 testers. The replication, as we said, is 1. And B initial, these are the budgets. Break down the initial, you start with this, then you go here, and the total budget is here. All this you multiply by 20 to give you 200,000 USD. So the gain is 5.691 divided by the number of years that your breeding scheme runs. This is 5, you divide by 5, you get 1.1. If you have any question, don't hesitate to email me. I'll be glad to explain into details so that you understand better. You may ask why it has increased here. Remember, you can see here the initial number is 1,308. It's very high compared to this initial number up here. And you see NI is the number which goes into the genomic selection 341. The selection intensity is too high. Okay, you see 351, then you select, you remain with 40. E281, you select, you remain with this one from the initial, this one. Then the optimum number in the first evaluation is this 40. Then when you go to the second evaluation, which is phenotypic, you select 10. We have 10 locations, and this is because these 10 locations are only in the first evaluation. Second evaluation, we don't have location. First evaluation, we have 3. Second evaluation, we don't have, because due to genomic selection, we reduced the evaluation and the number of years reduced. Therefore, the genetic gain across that years increased. So if we divide by the number of years, since we reduced the second selection, the years may be like we used it 3, and the annual genetic gain is 2 point something, while here is 1.14. So you see genomic selection increases the gains. And this has optimized your numbers, the number of testers, of which if you fumble, you may need to get these gains. And at the end, you misuse the funds available, and the results might not be good. My name is Wilfred Abinja. Kindly subscribe, like. I hope this was helpful.